Before docking with the International Space Station, what must a pilot of a space module first do? Put the money in the parking meter.
One diaphragm per mankind.
Whoa, didn't see you there. Welcome to Crash Course Astronomy with your host, Juli Neris. We're going to learn about quasars today. Hope you have a good time. Quasar, an astronomical object of very high luminosity found in the centers of some galaxies and powered by gas spiraling at high velocity into an extremely large black hole. The brightest quasars can outshine all the stars in the galaxies that they are near, which makes them visible at even distances of billions of light years. Quasars are among the most distant and luminous objects known. Quasars are apparently powered by gravitational accretion onto supermassive black holes, where supermassive means from roughly 1 million to a few billion times the mass of the Sun. The term quasar derives from how these objects were originally discovered in the earliest radio surveys of the sky in the 1950s. Away from the plane of the Milky Way galaxy, most radio sources were identified with otherwise normal-looking galaxies. Some radio sources, however, coincided with objects that appeared to be unusually blue stars. Although photographs of some of these objects showed them to be embedded in faint, fuzzy halos, because of their almost star-like appearance, they were named quasi-stellar radio sources, which by 1964 had been shortened to quasar. The optical spectra of the quasars presented a new mystery. Photographs taken of their spectra showed locations for emission lines at wavelengths that were at odds with all celestial sources then familiar to astronomers. The puzzle was solved by the Dutch-American astronomer Martin Schmidt, who in 1963 recognized that the pattern of emission lines in 3C273, the brightest known quasar, could be understood as coming from hydrogen atoms. An even bigger surprise was that continuing observations of quasars revealed that their brightness can vary significantly as short as a few days, meaning that the total size of the quasar cannot be more than a few light days across. Since the quasar is so compact and so luminous, the radiation pressure inside the quasar must be huge. The only way a quasar can keep from blowing itself up with its own radiation is if it is very massive, at least 1 million solar masses, if it is not to exceed the Eddington limit, the minimum mass at which the outward radiation pressure is balanced by the inward pull of gravity. This was named after English astronomer Arthur Eddington. Astronomers were faced with this. How could an object about the size of the solar system have a mass of about 1 million stars and outshine by 100 times a galaxy of 100 billion stars? Although the first quasars known were discovered as radio sources, it was quickly realized that quasars could be found more efficiently by looking for objects bluer than normal stars. This can be done with relatively high efficiency by photographing large areas of the sky through 2 or 3 different colored filters. The photographs are then compared to locate the unusually blue objects, whose nature is verified through subsequent spectroscopy. This remains the primary technique for finding quasars, although it has evolved over the years with the replacement of film by electronic charged coupled devices, or CCDs, the extension of the surveys to longer wavelengths in the infrared, and the addition of multiple filters that, in various combinations, are effective at isolating quasars at different redshifts. Redshifts are the displacement of spectral lines toward longer wavelengths in radiation from distant galaxies and celestial objects. Quasars have also been discovered through other techniques, including searches for star-like sources whose brightness varies irregularly, and X-ray surveys from space. Indeed, a high level of X-ray emission is regarded by astronomers as a sure indicator of an accreting black hole system. The number density of quasars increases dramatically with redshift, which translates through Hubble's law. This law states that the universe is constantly growing to more quasars at larger distances. Because of the speed of light, when quasars are observed at great distances, they are observed as they were in the distant past because light takes time to travel. Thus, the increasing density of quasars with distance means that they were more common in the past than they are now. This trend increases until look-back times that correspond to around 3 billion years after the Big Bang, which occurred approximately 13.5 billion years ago. At earlier ages, the number density of quasars decreases sharply, corresponding to an era where the quasar population was still building up. The most distant and thus earliest quasars known were formed less than a billion years after the Big Bang.